welcome IE students. My name is Carlos, and we're so glad you're here with us here at the Borns Technology Center. And I'm here to learn about waves.
Then there are microwaves.
And there's waves of light. It's so bright.
There are sound waves.
Okay, everyone, welcome. Science on stage. Let's make some noise this morning. All right. Great job, great energy. All right. And welcome to our online audience, wherever you're watching us from. Welcome to Science on Stage. I'm your host, Carlos, and we're going to have a great time today learning about waves, world of waves. Are you ready to learn some fun? Are you ready? Are you ready to breathe in more smoke? Yes, yeah, haze. Well, we have our star of the show today, straight from San Diego. He's a Padres fan, so haha. Straight. Go Dodgers, yeah. Straight from San Diego, we have the insurmountable, the incomparable Professor Matters. Here he is. Let's hear it for him.
All right, Carlos, thank you. High five, buddy. Go Padres. All right, welcome. Good morning. My name is Professor Matters. Today we're going to talk about sound waves, light waves, radio waves, microwaves, all kinds of things like that. You'll have to pay attention because along the way we'll be asking questions and you will provide the answers, all right? So, here I am with my little buddy metronome. It keeps time. I want to see if you can clap your hands each time that makes a click. Excellent. Thank you. All right. So this is wonderful. Many of the ideas we'll be talking about are as simple as clapping your hands, keeping time, keeping a certain frequency. Now you have cards out there, frequency, amplitude, spectrum, and wavelength. So each time we say one of those words, if you have that card, hold it up, okay? All right, so this is wonderful. Let's see, let me head out here a little bit. But we're going to talk about the world of waves, and I need Dr. Dynamite and Dr. Boom. Where's Dr. Boom?
Professor Matters, I hear you.
Doctor. There you are. Dr. Boom and Dr. Dynamite, also known as Rackus and Rufus here. That's awesome. That's awesome. So what have you got here?
Well, we have some tone tubes here, like wind chimes. Dr. Dynamite?
A snare drum here.
Awesome.
Wow.
They
Now,
make sound.
We were investigating the difference between membranes vibrating and tubes vibrating. Okay, and we've discovered a few things about the tubes, but the drum head we're still learning about.
Okay, so the vibrating is the important part?
Vibration, yes. The vibration is what makes these things emit sound, and then that's transmitted with compression waves going through the air to our ears.
To our ears, and then our brains interpret what we hear.
Right.
Very cool. Dr. Dynamite, do I smell something back at the lab?
That's my impulse generator. I gotta go.
The impulse
better go.
generator, you left it on.
Yeah, not
Oh,
again.
no.
Remember what happened last time? Back at the lab?
Yeah. Well,
Very good, Dr. Boom. So thanks for coming in.
Yeah. Oh, thank you.
Sorry we're late, but that's okay.
Yeah. Well.
The audience is here. We're going to talk about the world of waves.
And we're going to talk about the anatomy of a wind chime. So wind chimes are made with a certain technique. So if we hung the wind chimes like here, not much happens, right?
He does.
Hit it harder. It has a little ring. But if you hold it at a nodal point, which nodal point's up here, then we have this. And you can hear that quite clearly, okay? And if we hold it another nodal point, which is here, and so basically the pipe vibrates at the ends here, goes through nodal point, and then it vibrates in this section here, and then it vibrates here. So when I hit it here, it actually makes it vibrate in the biggest displacement area. So it's important to hold it.
Wow.
You never know with wind chimes, we could probably make them like even 3 times the height, but we have to change the diameter to make them work. So here's a nodal point here on this one. You can hear that ringing. And it's the one that extends out. Now, I found another nodal point the other day, and this one sounds like a church bell.
Oh, it does.
Yep.
Oh, wait a minute. Mission Inn Hotel. Did you borrow these?
I just borrowed it for today.
Oh, I hope they
We
don't.
have to take it back.
You better get it back
Otherwise,
in there.
the chimes won't be going
Won't
on
be after you,
at night.
no.
Yeah.
Very good, Dr. Boom. And you mentioned the word nodal, based on the word node, N-O-D-E.
Yes.
What is N-O-D-E?
I remember it says no displacement, no deflection.
No deflection.
No deflection.
Or no displacement.
No displacement, no deflection.
Excellent. Excellent. So node is where it's not vibrating.
That's right.
Or at least vibrating the least. Now, let's look at these characteristics of waves. We've all talked about these, and you're going to hold up your cards when I say, for instance, wavelength. Who's got wavelength cards? Hold it up. Wavelength is the length between, or the distance between, 2 similar portions of adjacent waves, okay? Now, how about frequency? Frequency is the number of times an event happens in some period of time, typically 1 second. So the number of events in 1 second, that's the frequency. How about amplitude? Amplitude is the height above what we call a zero or an equilibrium value, kind of like a mountain above sea level. That's amplitude. And if we get lots of different sounds or different colors of light or microwaves and all that, a whole bunch of it, we call it a full spectrum. Okay, very good. Very good. So hang on to those cards. They may be worthless someday. Worth something someday. Okay, it's all good. Now, what have you got here, Dr. Boom?
Well, I have a surgical tube, and we're going to demonstrate a transverse wave. Now, transverse wave is like an ocean wave on the surface, okay? You can have ocean waves and water waves underneath the surface, and that's like sonar and things like that. But an ocean wave travels across the ocean in a transverse way. So what that means is that the displacement is vertical, and the travel is across the surface, so it's at 90 degrees. And so I'm going to show you here a traveling wave, okay? And so a traveling wave, if I pull this up and I displace it, you'll see what happens at the other end, okay? There we go. And so I pick it up here positive, let's say, and it comes back negative on the bottom, okay? It inverts.
Dr. Boom, I could see that. You pulled it up there. When it hit here, it started out down. Do that again. Boom. It happens quick. You got to be good, but
right.
That's awesome.
And you see it reflects back and forth until finally it damps out and the resistance of the thing stops it. And so if I put my foot down here and then transmit, and so you see it's just the same.
Careful there. Nicely done. Nice.
Okay, so now what I'd like to show you is a fundamental frequency. Like these pipes here, when I held them at the nodal points, I excited a fundamental frequency of the pipe. Okay, and so this is the fundamental wave, the fundamental frequency of this surgical tube.
So you're talking about frequency, you got to be holding up your cards. And I see amplitude here.
Right.
So the equilibrium, or zero, is about here, and the amplitude of this, amplitude, is about this high.
That's right.
Awesome.
And so now if I double this and make it a full wave, I'm going to end up getting a nodal point in the middle, which is where the green flag should be, approximately. And so this is a full wave. And so you can see the wavelength here is going to be quite long. In fact, electrical wavelengths for your house are miles and meters and thousands of meters long. And so, but they're always changing. And so now I'm going to try and double this frequency.
All right, double. Can you triple it?
I don't think so.
Come on,
but,
crowd.
Okay, I got double
give
right
them
there.
Encouragement to triple it.
All right. So
Come on.
2 full waves.
Well, that's pretty good.
Yeah.
How about quadruple it? Can you quadruple it?
No, I don't think so. My arm's not that fast.
So one of the things we have used in the past is a sawzall. So if you're doing this in class, maybe you use a sawzall.
Yeah.
Very cool.
So we have another wave demo here. This one's called the Shive Wave Generator, and it was invented by Dr. Shive. And the Dr. Shive wanted to demonstrate electromagnetic waves to his students in college. Okay, and so let's see what happens here. I'm going to excite a wave, and Professor Matters will get it received over there. Now watch, it'll reflect off. It'll reflect, there it goes, and now it's coming back and reflecting back. See that? And so now if Professor Matters excites a wave from down there, and I excite one from here, we have 2 waves that are traveling across from each other, and they're going to go through each other, reflect off the ends, and then they're going to come back and go here. Okay, so now if we just continue to send waves across to each other, we would just do this. So now it looks all kind of discombobulated, right? But all these waves are forward and reflected waves. And they all will damp out because it's the resistance of the material that's making them damp out. But if they were not to damp out, they would just go on for infinity, but that's impossible.
Nicely done, Dr. Boom and Dr. Shive.
Now, that's impossible for these kinds of waves in matter, but if there's light waves in space, they continue until they hit something.
Oh.
And so light waves go back millions and billions of light years. That's why we call them light years, because it's how far light travels in a year.
Interesting. Thank you. Okay, now, Dr. Boom, if we talk about, in sound, we talk about compression waves. So compression is where you're squeezing things together, increasing the density, or increasing the pressure, or increasing whatever, and that's how sound comes out of my voice, goes to your ears, and you can, or the microphone, and you can hear that. Now, what have you got here from the lab, Dr. Boom?
Well, from the lab, I brought a sound wave visualizer. Now, what this is 2 speakers. They're 400 watts each, and they're subwoofers, so they're low frequency. And I have a tube here. The tube is just filled with air, and there's little styrofoam balls in here, and they're across the whole tube. And I have some screens on the end so that the styrofoam balls stay in the tube and don't go into the speakers. And then, hooked up to the speakers, I have a thing called the co-oscillator, which is a little musical device, okay? And I use it to play the low frequency sounds like the bass sounds. Okay, I hope I didn't. Okay. So these are standing waves, and you can see that they stand up, literally, and they move around a little bit. Now that's a traveling wave. Look at that big one there coming across. I hit resonances as I go through the scale. There's some standing waves there. So you can visualize the waves. So now what happens here is the styrofoam balls go up in the rarefaction zones, and they are pushed away from the. Oh, I have a little mode here. They are pushed away from the high pressure zones.
All right. Nicely done, Dr. Boom. That's all from the lab. So this is something they could make in class.
Oh,
Two
yeah.
speakers, a plastic tube, and some microspheres. Very nice. Thank you. I like that. Now, we talked about having the microspheres and the air in there because compression waves need something to compress. They need a medium. It might be wood, it might be glass, it might be air. If there's no medium, we have no sound. So the question, can you hear in space? You can't hear in space. You can't speak in space because there's too little air or medium in which to make sound. So before you put that on, this little sphere here is just open to the air. Open to the air. There's air inside of there. Why don't you go and turn that speaker on? There's a speaker and a microphone. Okay. Now Dr. Boom is going to hook up this tube, and that tube is connected to a vacuum pump that's going to evacuate that. Much to your happiness. The air is going out. The air is going out.
Right, so it's getting less dense inside. So it's getting more like space where there is no air. So there's no medium for the sound to be transmitted. And so just a short distance from the microphone here and the speaker here, there's no air really to go. You might hear a little soft sound there, but that's because the wires are connected to the same membrane as the microphone.
So that's pretty cool. So you cannot hear if there's no medium in which to compress.
That's right.
Right? So let me switch this off. I'll close this valve. You can turn off the pumping. You can take the tube off. It'll still be evacuated until we open this valve. And I think your siren is still connected, right?
Still going.
Still electrically connected.
There you go.
Pretty annoying. All right, very good, Dr. Boom. So the idea is you need a medium. You need a mass. You need something to compress if you have compression waves. Very cool.
So I think we have a Slido question here.
Yeah. Thank you. So, for those in the remote world, a Slido question is coming up. And for you here, we're going to ask you a question as well. Okay. So, a sound wave needs a medium, some kind of matter, and therefore cannot travel through which of these? Water, evacuated space, glass, or air? Sound waves cannot travel. Glass, evacuated space.
All right.
Evacuated space is the answer. It cannot travel through air because there's nothing to compress. And sound is a compression wave. Very cool.
Okay.
All right.
So now our next demo, we're going to play you a sound wave sweep. And the sound wave sweep, we want you to listen to the waveform and imagine what instrument that sounds like. What instrument has that tonal quality?
Oh, square wave. I see
Square wave.
square.
Yes.
triangle. See the triangle? Awesome.
Sounds like the sirens at my house.
Very
Okay,
cool.
see, that's a sawtooth wave.
And yeah, sawtooth. So these different waves are not just the nice, smooth, what we call sinusoidal waves. They can be square, they can be triangle, and they can be what he calls sawtooth there. Now, we're going to go from sound into the electromagnetic spectrum. The electromagnetic spectrum includes light and radio waves and microwaves and gamma rays and things that we use every day. Electromagnetic energy is made up of an electric part and a magnetic part. And some of the cool things, you already work with this. Many of you have polarized sunglasses. Polarized sunglasses. And what that does is that reduces the amount of glare, let's say, that comes off of the surface. And we can do that. Dr. Boom.
Yes.
Yes. So he's going to hold one of these polarizing sheets or polarizers up to his face. You see him? Yeah, pretty scary.
Ready for
there.
Halloween.
Pretty scary. I'm going to hold another one up. Very simple. Very simple. You can still see him.
Now you see me.
Look over there to the left a little bit. Over here to the right a little bit. Okay? And now, for all of your enjoyment, I'm going to make him disappear. Just by doing this.
I'm still in here. I'm still in here.
Okay, look to the left. Okay.
Where'd he go? Where'd he go?
Where'd he go? Where'd he go? So, with a very simple couple of special pieces of plastic, one could make, you could make these into like curtains at home. I mean, effectively curtains that
Or windows.
change. Yeah, windows, but like a window shade that keeps light out and keeps things in. So that's the concept of polarizers using electromagnetic radiation. So some part of that. Now, there's also things that we don't see. Much of the electromagnetic spectrum we don't see. We don't see microwaves. We don't see heat or infrared.
Or radio waves.
Or radio waves. We don't see radio waves. That's right.
Or X-rays.
What have you got? Marriott Hotel. Okay. What have you got here?
I borrowed this from the lounge upstairs, but I'll take it back.
Okay. So this is the door of a microwave oven. Who here has ever used a microwave oven to watch their burrito or pizza or something go around inside of there, right? The door, next time when you go home today, take a closer look at your microwave oven door. It has little tiny holes in it that allows visible light through, but it acts as a wall for microwaves. Because what would happen if it allowed microwaves through as you're looking up through there looking at your burrito?
Your eyes would cook.
Your whole face would cook.
That too.
You'd look like your burrito
But I think the eyes are most vulnerable.
after a while. Anyway, so there's windows and there's walls. Windows allow transmission. Walls block that transmission. Very cool. Now, many of you are familiar with this kind of a setup up here where we've got infrared or thermal or heat. If you hold your hand to your forehead, what do you feel? You feel heat, right? So, we have a little camera here that's an infrared camera, and we're looking at you right now. Yeah, wave. Go ahead and wave. It can't see visible, and it's a little out of focus, but that's okay. It wouldn't be able to read the letter A if it was right in front of it, okay? But some of its properties are pretty cool. So here's a simple piece of plastic. Is that shiny? See the reflection? So this will reflect visible light. It also reflects infrared, but the key thing is it transmits visible light. But let's see if we can look at the infrared you have out there, or if it blocks it. Totally blocks it. Totally blocks it, okay? But check this out. Is this a window or a wall for visible light? It looks like a wall, right? You can't see how many fingers I'm holding up. But looking through here, there's 3, okay? So the idea of windows and walls, scientists and engineers need to know how the different parts of the electromagnetic spectrum interact with matter so that we can make an appropriate window or wall. Very cool. Whether it's microwaves, infrared, gamma rays, radio, all kinds of things. Very cool.
Want to have somebody stand up, maybe?
Oh, maybe so. You want to stand up? Yeah, and then just step right over here. And we're going to see where you were sitting. Oh, come back.
IR camera, please.
Come back. There you go. That's where you were sitting. Right there. Okay. Hot stuff. Hot stuff. We're all familiar. We're all familiar when we sit down in a chair that was someone else was sitting in just a moment before and you feel heat. Well, here we can actually see it. Okay. All right. So we have a question. I think we have a question coming up here. Lido question. Are you ready? Thank you.
Enter the code.
All right. You want to read this one?
Your hands not only reflect light, but electromagnetically, they also emit a wave. So is it germs? Is it skin? Is it infrared light? Is it air? So it looks like the infrareds have it.
Infrared light.
Infrared light.
For heat, but travels through space. And you do not need a medium for that. We don't need any air. We don't need any water. We don't need anything like that. Electromagnetic energy that travels through space.
That's correct. And so there's telescopes that just look at the infrared universe. And everything that in the universe that has heat, it sends these infrared waves out. They travel for millions and billions of miles. And this telescope looks at those things so we can see stuff that's hidden behind clouds that we can't see with visible light, which is really cool stuff.
That's true. That's true.
Now I have another demo here. This one here uses electricity from the wall. Now the frequency of the electricity coming from the wall is 60 hertz, 60 cycles per second. Right, and Hertz was the guy who worked with frequency, and it's named after him. So it's not the car rental place. And so what I'm going to do here is I'm going to plug this into a wall, and the current in this coil, we have about 100 turns. The current's going to go around and around and around, and it's going to, let's see, it's going to go this way. So the North Pole would be here, and the South Pole would be here, and that cycle, and then it's going to reverse and go this way. So the North Pole will be here, and the South Pole will be here. So it's switching back and forth. The poles are switching back and forth 60 times a second. Now I'm going to put this on top of the aluminum plate here, and the aluminum plate, the magnetic field will induce a current in the into the aluminum plates, and it's called the image current. So it'll go basically the same direction, except that it'll make a pole that's pushing back, which will be a repelling pole, which will be like pole, and it will have the same frequency. And so I'm going to plug this in over here. And then I'm going to turn it on. I have to hold it because it's pretty active.
Whoa.
See, it's floating here. It's kind of bouncing a little bit. If I turn it off, I can make a hopping coil out of it. And so this is kind of like if you sat on it and you could ride it around the city here, that would be cool, right? Just like Back to the Future. Okay. I have to, this thing gets pretty hot, so I'm going to turn it off right now. And so we have another demo for you that has a single pulse of current, which produces a single magnetic field that does not have a frequency associated with it. And so it's like a drum head in that sense. And so Dr. Dynamite, we might experiment with this.
Back at the lab?
Back at the lab, yeah. So what I have here is an aluminum can on top of this coil, and I have a power supply and a power supply and a capacitor in the bottom. Now, a capacitor is sort of like a battery, except the capacitor discharges all of its energy really fast. And so I'm going to charge this up to about 2,000 volts.
2,000 volts?
2,000 volts. There we go, 2,000 volts. And I should just about hit the ceiling here.
Nice.
Okay, up a little more. Okay, 2,000 volts. Should we go higher? Yeah? How high should we go? Let's see, we'll go to 3,000 volts.
3,000. That's more than enough.
You think we'll hit the ceiling?
No, I won't hit the ceiling.
Okay, he says it's okay. Ready, give me a countdown. 3, 2, 1. Whoa. We don't want to hit the screen here.
We might hit that.
Yeah.
Well, that was very cool. So you put in electrical current and it made magnetic field. And, what are you doing here?
Well, I'm going to do another can.
Okay.
I'm going to launch another can. This time I'm going to put a lid on it, and we're going to charge it up to 5,000 volts.
5,000 volts.
5,000 volts. And so, all right, let's
2,000.
see.
2,000 higher.
5,000
higher. 3,000 higher. 4,000 higher.
5,000. Okay, we're at 5,000 volts. Here we go. Are we ready? 3, 2, 1.
Oh, man.
Look at that.
Very cool. Now, Dr. Boone, here's something that's kind of interesting. The bottom of the can felt that magnetic impulse so quickly that it actually smashed the can before it actually left this magnet. Happened very quickly. This is just like the Padres smashing the LA Dodgers. So, very cool. All right.
All right. So we have one more demo for you. This is our finale, basically. You've been a great audience. Can we have our poppers up here, please? Now these poppers they're 10 bottles. They're filled with a combustible fluid.
Thank you. Thank you.
And I have a Tesla coil in my hands here. Tesla coil puts out 30,000 volts here, and watch what happens. So this is 10,000 volts, 10,000 degrees centigrade, and that's the arc, okay? And so this has a spark plug in it, combustible fluid, a cork in the end, a little surprise at the top, and we'll see what happens. Are we ready? Are you ready? 3, 2, 1.
All right, Dr.
Thank you very
Boone.
much.
Awesome. Very good.
Okay, well, a round of applause for Dr. Boone, Professor Matters. Hey.
Thank you.
You got some stuff to come on stage. We enjoyed spending this time with you and teaching you about waves.
All right, thank you.
And we're going to do what a wave does. We're going to take a bow. Ready?
Thank you very much. Good job.
Let's take a bow. Ready? 1, 2, 3, bow. We bow. And we come back up. Wave. Thank you for learning today with us. We hope you have a great rest of your day. If you're staying at STEPCon, awesome. If you're going back to school, make sure you tell someone about what you learned. Keep that card of yours that we got. It's a memento. It's priceless. All right. Have a wonderful day and goodbye, everyone. Bye. Bye-bye. Love you, but bye-bye. Thank you for being here. Love you, but bye-bye.